Hello students, we have come to the end of the semester, the spring 2021 semester. It's been quite a journey. Here are a few topics that you need to focus on in order to do good on the final examination. So here we go. The first topic is from current electricity. So you have a circuit right there with a battery or an electric cell, 5 volt. You have two resistances connected in series. Whenever resistances are connected in series, you know that the current flowing through them are the same. So currents in series are equal. But the potential drops are not. So if you add the potential drops across the resistors, you must get the total potential drop of the source, which is what we're going to do. Also remember that the end A is going to be at a higher potential because it's connected to the positive of the battery, while the end D of the other resistor being connected to the negative of the battery is going to be negative, which means C is at positive and B is at negative. That's why we say when you move from A to B, there is a potential drop, which means the potential decreases. Once again, when you move from C to D, the potential drops. If you add the two potential drops, you must get 5 volt. So let's do this. What is the total resistance in the circuit? How are the resistors connected? They are connected in series. So, to find the total resistance, just add them up. That means the total resistance is 5 ohms. Okay? So, the total resistance in a series circuit is simply the sum of the resistances, which gives us 5 ohms. The next question is, what is the current flowing through these resistors? According to Ohm's law, current is voltage by resistance. Therefore, the voltage is 5 volt, the resistance is 5 ohms, and you get 1 ampere. So what is the current through the 1 ohm? It's 1 ampere. What about the current through 4 ohms? It's also 1 ampere. Why? Because when the resistors are in series, the current flowing through them are equal. Okay, so if that be the case, let's find the potential drop across the 1 ohm. How do you find the potential drop? Potential drop is the product of current and resistance. The current is 1 ampere. The resistance is 1 ohm. That gives us 1 volt. Similarly, the potential drop across CD, which is the other resistance, is 1 ampere times 4 ohms, which gives us 4 volt. And there you see that if you add the two, 1 plus 4, you get 5 volt, which is the voltage of the battery. So that is very important to know, which brings us to the second topic. And it deals with resistance of a conductor. The resistance of a conductor is given by this formula, R is equal to rho L by A. Rho is a constant for a material. So if it's copper, it has a certain value. If it's aluminum, it has another value. So rho is a constant. That's important. L is the length in meters and A is the area of cross-section in meters squared. Now, normally, cables have a circular cross-section, and therefore, the area is calculated using pi r squared. That's why you have pi r squared. Of course, r, little r, is the radius of the cable. Okay, so in that formula, R is the resistance, rho is resistivity, which is a constant, L is the length, and A is the area of cross-section. So, here's a question. If you take a copper cable of a certain length and a certain area of cross-section, and if you are strong enough to stretch the copper cable to double its length, you know it's going to get thinner. And let's say that the area of cross-section is going to become half. How do I know? Because the volume has to stay constant. So if you stretch a cable to double its length, automatically the area of cross-section is going to become half. So the question is, what happens to the resistivity of that cable? Give it a thought. Resistivity is a constant. It depends on the material and only on the material. When you stretch the cable, did you change the material? No. That means resistivity is the same. Okay, the next question is, what happens to the resistance of the cable? Did that change? Let's think about it. When you make the length double, the resistance also becomes double on that account. But when the area of cross-section becomes half, the resistance again doubles. That means the resistance quadruples. The resistance becomes 4 times the original value. Here is the third concept. This concept deals with the force acting on a charged particle moving through a magnetic field. The force acting on a charged particle moving through a magnetic field. So F is the force, the magnitude of the force, Q is the charge of the particle in coulombs, V is the velocity of the particle, caps B is the strength of the magnetic field in Tesla, and theta, of course, is the angle between the velocity and the magnetic field. Let's give it some thought. So first of all, let's imagine it's a positively charged particle. And let's say that the magnetic field is set up from my left to my right, that way. And the particle is also moving from left to right. That means the velocity of the particle is parallel to the magnetic field. What's the angle? The angle is 0. And sine 0 is 0. What does that mean? No force acts on the particle. So whenever a charged particle moves parallel to a magnetic field, no force acts on it. So the next question is, when does maximum force act on it? The answer, if the angle between the velocity and the magnetic field is 90 degrees, or if the particle moves perpendicular to the magnetic field, then the force becomes maximum. So again, if the magnetic field is from my left to right, but the particle is going away from me towards the screen, you see, the angle is 90 between the magnetic field and the velocity. In this case, the maximum force acts on the particle. What is that maximum force? It's going to be QVB. Why? Because sine 90 is 1. Okay? So that's the magnitude of the force. Well, now what about the direction of the force? The direction of the force is given by the right-hand rule. Right-hand rule. Fingers show the direction of velocity. So I was imagining that the positive particle is moving away from me. So that's why I'm holding the fingers of my right hand towards the screen, away from me. So that's the velocity. The palm should give the direction of the magnetic field. And since the magnetic field was from left to right, I have to point my palm that way. Now it's okay. Velocity, magnetic field, and the thumb gives you the force acting on the positive particle. That's the right-hand rule. But remember, this only applies to a positive particle. So the question is, what if it's a negative particle? Well, then you take exactly the opposite direction, which means if the negative particle was moving away from me, and the magnetic field was set up from my left to right, then the force acting on it would be upwards. This can be illustrated. There are some points here. You can read that. That's everything that I said. And the direction of that force is given by the right-hand rule that you see there. Okay, so those 5 points are actually the summary of everything that I said. And this gives you the right-hand rule. Remember to use the right hand, fingers pointing in the direction of velocity, palm pointing in the direction of magnetic field. The thumb gives you the direction of the force acting on a positive particle. If it's a negative particle, remember to take it opposite. That's the next concept. Brings us to the next one. I wanted to give you one more point about this, which is very important. Now, what happens to the velocity of this particle? When a force acts on it, we may think that it's either speeded up or slowed down. But remember that the speed of the particle does not change. Only the direction changes. What do I mean? If a particle enters perpendicular to a magnetic field, so particle enters perpendicular to a magnetic field, then the magnitude of its velocity will not change. So if it's moving, if it's entering at 10 meters per second, even though a force acts on it, its speed will continue to be 10 meters per second, only the direction of motion will change. Okay. Bringing us to capacitance. Capacitance of a parallel plate capacitor. You know what a capacitor is? Two metallic plates, let's say aluminum plates, with an insulator between them. That's a capacitor. That's a parallel plate capacitor. Two aluminum plates with an insulator between them. The insulator is called a dielectric. And the dielectric has a constant, which is called the dielectric constant, and that is K. So K is the dielectric constant. A is the area of the plates. Typically, both of the plates have the same area. So it's just the area of one plate. And if they're not equal, then take the overlapping area. So A is the area of the plates. Epsilon naught is the permittivity of free space or vacuum. It's 8.85 times 10 to the negative 12. The units are right there: Coulomb squared, Newton raised to negative 1, meter raised to minus 2. You need not cram all the units. Neither do you need to memorize the constants. It'll all be given to you. You just need to know what they stand for. D is the distance between the plates. So those are the 4 factors on which capacitance depends. So how could you increase the capacitance? Quite simple. There are 4 methods. Number 1, use a material which has a higher dielectric constant. Number 2, have an increased area for the plates. Number 3, decrease the distance between the plates. Well, there are only 3 ways of increasing the capacitance, because the 4th one, epsilon naught, is an absolute constant. That's why. So that's the formula for capacitance of a parallel plate capacitor. All right, I just remembered. What quantity stays the same when capacitors are connected in series? Yes, it's the charge. The charge stays the same. So if you have any number of capacitors connected in series, all of them will have the same charge. Just like all resistances connected in series have the same current. So there it's current for resistors, here it's charge for capacitors. What quantity stays the same whenever resistors or capacitors are connected in parallel? Yes, it's the voltage. Any electrical component connected in parallel, whether it's resistors or capacitors, whatever, the voltage will be the same. Right. So here we have three capacitors connected to a battery, and let's say they're 1, 2, and 3 microfarad. Just made up some numbers. And this is a 5-volt battery. And we want to find the charge on the 1 microfarad capacitor. That's a question. How do you find the charge on the 1 microfarad capacitor? Well, first of all, we know that the charge on the 1, 2, and 3, they will be the same. How do you find that? First of all, find the equivalent capacitance. How do you find the equivalent capacitance in series? Remember, it's 1 over C is equal to 1 over C1 plus 1 over C2 plus 1 over C3. You notice the difference between capacitors in series and resistors in series? Okay. So do the calculation. You get 1 by 1 plus 1 by 2 plus 1 by 3, and that is 1 over CS. And therefore, you got to take the reciprocal of that, which will give you 0.545 microfarad. Okay, once you get the equivalent capacitance, we know that the voltage across that capacitance is 5 volt, don't we? Because we've replaced all the three with a single capacitance whose value is 0.545 microfarad. So once we know that, we can calculate the charge simply by multiplying the capacitance with the voltage. So 0.545 times 5 gives you 2.73 microcoulomb. That's the capacitance, the charge on all three capacitors, because the charges are equal. What about the voltage? Let's find the voltages on all three of them. The voltage on the first one is its charge divided by its capacitance, all right, which gives you 2.73 volt. The voltage in the second one likewise is the charge on it divided by its capacitance, which gives you 1.36 volt. The third one, 0.91 volt. Add them up, what do you get? 5 volt. There you go. Capacitors connected in series, the charges are equal, the voltages are not, but when you add the voltages, just like in a resistor, you should get the voltage of the battery. Next up, LCR circuits. So the combination of a resistance, capacitance, and inductance. Before we get to that LCR circuit, let's remember a very important thing, that whenever you apply an alternating voltage to a resistance, the current that flows through the resistance will be exactly in phase with the voltage. That means the current will rise and fall with the voltage. Remember, it's an alternating voltage, so it goes up and down, and the current will follow likewise. But that's not the case for an inductance. For an inductance, the voltage leads the current by 90 degrees. And for a capacitance, it's the other way around. The current leads the voltage. How do you remember that? Eli loves ice. Okay, let me break it down. Eli. E stands for EMF or voltage. Because I wrote that first, that means it leads. Voltage leads the current. In an inductor, the L stands for inductance. So that's how you remember that. I wrote the E before the current. So the voltage leads the current by 90 degrees or pi by 2 radians. Okay? For a capacitor, I wrote the current I before. So that means the current leads the voltage by pi by 2, 90 degrees. That's important to know. Also important is to know how to calculate the reactances. Now, what do you mean by reactance? Reactance is exactly like resistance. It's measured in ohms. So, what is the reactance of a capacitance? It's simply 1 divided by 2 pi Fc. F is the applied frequency of the voltage, C is the capacitance. And XC is in ohms. What about inductive reactance? It's going to be 2 pi F times L. Again, F is the frequency in hertz. L is the inductance in henries. Okay, got to remember all these units. Capacitance is in farads. Inductance is in henries. Okay, but the reactances are going to be in ohms because the reactances are just like the resistance. So that's why it's measured in ohms. All right, so we looked at these three individually, but what happens if you connect all three of them? Resistance, inductance, and capacitance in series, and then you apply an alternating voltage. Well, then together they're going to act differently at different frequencies, but there's going to be one particular frequency at which the current becomes maximum. That frequency is called the resonant frequency. Resonance means maximum. In this case, maximum current. And how do you calculate the maximum current? I mean, calculate the resonant frequency. It's 1 by 2 pi square root LC. Remember to have inductance in henries, capacitance in farads. Shall we work out a question? Okay. I also wanted to point out that the resonant frequency does not depend on the resistance. It's independent of the resistance because that resistance is not anywhere in this formula. So if the inductance is 1 millihenry, which is 10 to the negative 3 Henry, and the capacitance is 1 microfarad, which is 10 to the negative 6 farad, then let's calculate the resonant frequency. Just be careful, put in the calculator, you get it as 5032.3 hertz. What is resonant frequency? It is the frequency at which the current becomes maximum, or the impedance. Not written down the formula for impedance, but remember, impedance becomes minimum. Now remember that on the final exam, the concepts are more important than calculations. So you got to be listening very carefully. I hope you are. The next concept is that of an electric field. How do you set up an electric field? One of the easiest methods to set up an electric field is to have two metal plates, one charged positive, the other negative. Oh, just like in a capacitor. But remember that the direction of the electric field is always from positive to negative. So the electric field is always from positive to negative. Because the electric field is defined as the direction in which a positive particle would move. That's why. So now here is the next question. What if you have a positive particle kept on plate A? So that's plate A, that's plate B. Think about it. Does the positive particle want to stay here? No, surely not, because it's going to be repelled by the positive charge and attracted by this negative charge. So it's going to automatically move from plate A to plate B, showing that the potential energy is lower at B. Very important point is to remember that anything always moves from higher potential energy to lower potential energy. Let me give you an example. If you have an object kept at a certain height and let go, it's going to drop down. I know it's because of gravitational force. But on the other hand, it's also because it's going from higher gravitational potential energy to lower gravitational potential energy. There you go. So in the same way, this positive particle is going to move from positive plate to the negative plate. So you know that the potential energy is higher on plate A, potential energy is lower for this particle on plate B. Now you're thinking, why is this guy telling us this? It's because if it's a negative particle, it will move in the opposite direction. So for a negative particle, where is the position of higher potential energy? You got it. It's on plate B. And the position of lower potential energy is plate A. Why? Because it automatically moves from the negative to the positive plate. So I hope you understood the idea of potential energy. But I want to cap it off by asking you this. Generally, where is the potential greater? I'm not talking about potential energy now. Potential is greater on the positive plate. That's why we call it positive. Okay, so potential is different from potential energy. Potential energy depends on the type of charge, whether it's positive or negative. Potential does not depend on the charge. Potential of a positive plate is always higher than the potential of a negative plate. But when it comes to potential energy, it depends on whether it's a positive charge or a negative charge. I hope that makes sense. Right. Okay, so that's what I'm writing here. For positive charge, there you go. A is higher potential energy. B is lower potential energy. For a negative charge, A is the lower potential energy. B is the higher potential. I told you that. Next up, you have a transformer. What is the principle of a transformer? It's mutual induction or electromagnetic induction. What are the parts of a transformer? Well, you have two coils, primary and the secondary. So you have the primary here, the secondary here, and they are wound on either side of an iron core. Okay, so those are the three parts, primary, secondary, and the iron core. And transformers only work on AC. Why? Because if you give DC to the primary, since it's a constant current, the magnetic field is not going to change and there will be nothing on the secondary. But if you give an alternating voltage, then since the alternating voltage is changing continuously on the primary, you will get continuous electromagnetic induction and a voltage on the secondary. What are the formulas you need to remember? Vp and Vs are the voltages on primary and secondary. Np and Ns are the number of turns on the primary and secondary. Here is a direct ratio. Vp by Vs is equal to Np by Ns. Easy to remember. So if it's a step-up transformer, then the secondary voltage is bigger. If it's a step-down transformer, then the primary voltage is bigger. But there's also another formula. The power in the primary is equal to the power in the secondary. How do we calculate electrical power? Oh, it's the product of voltage and current. So that means the product of the primary current with the primary voltage should be exactly equal to the product of the secondary current with the secondary voltage. There you go. That's all you need to know. Parts of the transformer. That the transformer only works on AC, because otherwise there's no electromagnetic induction. And these two formulae. That's all. And what is a transformer used for? It's used to change the voltage. Yes. It's used for transmission purposes. It is used to change the voltage. The next concept, electromagnetic waves. What is an electromagnetic wave? It's an electric wave and a magnetic wave in perpendicular directions and also perpendicular to the direction in which the electromagnetic wave is traveling. Oh, did that sound confusing? Look at the diagram. You have X, Y, and Z axis. If the electric field is along the Z, the magnetic field is along the X, the electric field along the Z, the magnetic field is along the X, then actually the wave is traveling along the y-axis. All three are mutually perpendicular, something like that. All three are mutually perpendicular, okay? That's what I mean. And how do you calculate the speed of an electromagnetic wave? Using this formula. C is equal to 1 by square root mu naught times epsilon naught. Mu naught is the permeability of free space. Epsilon naught is the permittivity of free space. Here are their values. And if you put those values down and calculate, you're going to get 3 times 10 to the 8 meter per second. What does that mean? That is the speed of all the regions of the electromagnetic spectrum. Is that the speed of X-rays? Yes. Ultraviolet rays? Yes. Visible light? Yes. Infrared? Yes. All right, no kidding. Radio waves? Yes. All of those regions of the electromagnetic spectrum have the same speed. Do they all have the same wavelength? No. Do they all have the same frequency? No. Do they all have the same speed? Yes. And you got to remember the order in which the wavelength increases or decreases. Just remember the order of the regions of the electromagnetic spectrum in the order of either increasing wavelength or decreasing wavelength. And I just gave you an example of the visible region. I wanted to talk about the visible region where you have the colors from violet to red. The approximate wavelengths are for violet 400 nanometer and for red 750 nanometer. That's electromagnetic waves. What do we have next? Oh, we have a huge topic where we talked about concave and convex mirrors and lenses. So mirrors, the phenomenon is reflection. Lenses, it's refraction. So remember that it's completely different. Mirrors reflect, lenses refract, means the ray goes through. But when you look at properties, the concave mirror is just like a convex lens. Concave mirror, convex lens. What are the similarities? Both have a real focus, which means they can produce a real image and they can also produce a virtual image. So they produce both real and virtual images. But the convex mirror and concave lens, they have a virtual focus and can only produce a virtual image. Another thing to remember is that all real images are inverted. All virtual images are upright. I told you, all real images are inverted, all virtual images are upright. And then you have the formulae that I'm going to write now. Virtual image. Oh, when does the concave mirror and the convex lens produce a virtual image? It's when the object is between the focal length and the lens. So if this is the convex lens, and if this is the focus of the lens, if you have the object anywhere here between the lens and its focus, then you get a virtual image. Any point outside the focus, you're going to get a real image. That's true for both concave mirror and convex lens. Okay. Well, I think I told you that all virtual images are upright and all real images are inverted. I think that's the third time. And then the law of distance is 1 by do plus 1 by di is 1 by f. Do is the object distance, di is the image distance, and f is the focal length. This formula is true for mirrors and lenses. But remember that if the problem is about a convex mirror or a concave lens, f must be taken as negative because the focus is virtual. All right, so if it's a convex mirror or a concave lens, both of them are also called diverging. Diverging mirror, diverging lens means convex mirror, concave lens. And for both, F is negative. Just remember. There's also a formula for magnification. That formula has a negative in it. M is negative di by do. What does the negative sign show? It shows that the image is inverted. The image is inverted. That's what the negative sign shows there. Bringing us to refraction. And in refraction, refraction is the bending of light when it passes from one material into another. All that stuff which you have studied. We don't have time to go into details. Remember, this is just a review. So I want you to remember that refractive index means the amount of bending. Refractive index is the amount of bending. And that can be calculated in three ways. So let's say we're talking about light moving from air into water. Air into water. So the refractive index of water would be the speed of light in air divided by the speed of light in water. Okay, that's one definition. The second one is refractive index is real depth by apparent depth. What do you mean? So if you look at a swimming pool from outside the swimming pool and try to estimate its depth, it's always going to look shallower than it is. Technically, if it's 4 meters real depth, it will only appear to be 3 meters deep. That's dangerous. Did I say 4 meters and 3 meters? Yes. What do you get if you divide 4 by 3? You get 1.33, which is the refractive index of water. So, if it appears to be 6 meters, then the actual depth or the real depth is 8 meters, because 8 by 6 gives you 1.33 again. There it is. The third method of calculating refractive index is using Snell's law. N1 sine theta 1 is N2 sine theta 2. Here's a quick example. It's going from air into some material. Oh, I think I took glass because I gave you the refractive index is 1.5. So if it's going from air into glass and the angle of incidence is 50 degrees, can we find the angle of refraction? Easy. Just 1 sine 50. Why did I put 1? Because that's the refractive index of air. And then 1.5 sine theta 2. We're looking for theta 2. Put this into your calculator and check if you get theta 2 as 33.3 degrees. If you do, you know how to apply Snell's law. So there are 3 ways of calculating the refractive index of any material. Those are the 3 formulas. 1, 2, 3, done. Okay, I'm back here again, vanished just for a bit. And this is about interference. And here you have a setup of 2 slits separated by a small distance, d. And then you have a screen and you have light coming in through the 2 slits. And on the screen, we get dark and bright regions. Those are called interference bands. And then we're going to explain this. So little d is the distance between the slits. Caps D is the distance between the slits and the screen. And we're going to consider a particular point P right there. And waves from the top slit reach P along the path AP, while waves from the lower slit reach P along the path BP. Now, isn't there a path difference? Yes, because the path BP is bigger than the path AP. Actually, the path difference is going to be given by this. And the path difference depends on how far away the point P is from the center of the screen. So let me label that. So that's the center of the screen. O is the center of the screen. And if this point P is y meters away, then the path difference is given by y little d by caps D. Okay, that's the path difference. So that means if you keep going higher and higher, the path difference increases because y increases. And depending on at what point you're looking at, you might get brightness or darkness. The condition for maximum or brightness is that the path difference should be equal to m lambda. Lambda is the wavelength of the light coming through. For minimum, which is darkness, the path difference is m plus half lambda. M can take values 0, 1, 2, 3, etc. Remember that if m takes value 0, then you are going to get, like in this formula, if you put m is equal to 0, the right-hand side is 0, so the left-hand side has to be 0. That means there is no path difference, which means we are talking about the point O, because that's the only point at which they both travel equal paths. Are you getting what I'm trying to say? Because AO is equal to BO. So what do you have at the center of the screen? Definitely it's bright. On either side of the center you have dark, and then followed by more dark and bright bands. Okay? And this is now thin films. So what is that? Let's imagine that you have a thin film of oil floating on water. So that film of oil will spread out so thin, it'll just be like an atom thick. And when light shines into that thin film of oil, a part of the light is reflected, while another part is refracted. And the refracted part gets reflected from the lower part of the oil. Remember, it's water here, and this is oil. Okay? So it gets reflected and then comes out. Let me draw that. There you go. And you're watching this from above. Let's call this A, B, C. So there are two rays, 1 and 2, reaching the eye. Which ray travels a greater path? Surely ray 2. Why? Because all the way up to A, they are together, then they split. Ray 1 went straight to the eye, but ray 2 had to go down through the oil, back up, and then to the eye. So what's the path difference? It's approximately twice the thickness of the oil film. That's very approximate, and that's all you need, because it's going down by t meters, coming up by t meters. So the approximate path difference is 2 times the thickness of the oil film. And from there, we can get the conditions for maximum and minimum. Okay, so the path difference is 2t. Okay, it's AB plus BC. Come on now, which is T plus T. But there is an important point. That is in oil. So you got to give it due credit. Ray 1 is traveling through air, while ray 2 is traveling through oil, where the speed is lower. So you got to give it more credit. How do we do that? We multiply the path by the refractive index of oil. So see that. So instead of 2t, that's 2t in oil, which becomes 2t times n in air. So comparing apples to apples, you got to multiply it with the refractive index of oil. Again, so path difference is 2nt, where n is the refractive index of oil. And for maxima, this path difference should be equal to m lambda. That's all you got to remember. Okay? So if you're looking at it from a point, and if a particular wavelength produces the condition or satisfies the condition for maximum, you see that color. So that's why when you look at different points, it's going to appear differently colored. Are we on the last one? I think I gave you an example here. Let's assume that lambda is 650 nanometer, which is 650 times 10 to the negative 9 meter, and m is equal to 1, so it's the first order. Simple calculation shows that, okay, the thickness of the oil film, that's what we're trying to find. So 2 times, I assume that the refractive index of oil is 1.2, it will be given to you. And we're trying to calculate the thickness of the oil film for what? In order for us to see the red color, in order for us to see this wavelength, what should be the minimum thickness of the oil film? And that's what you're getting. it should be 270.83 nanometer. Wow, that's a real thin film. So that is when you would see that particular wavelength. If you want to see another wavelength, well, the thickness should be a little different. I hope that makes sense. Thank you. This is me signing off. It's been a great semester. Take care and good luck.